Okay, lesson 11 was parallel. To find Q, it was still X of L over R in series, right? And to get P, you take Q squared times the resistor in series to get RP, right? Or if you know X of L, and you know Q equals X sub L over R in series equals R in parallel over X sub L. Okay. This is always true, series. This is why I wanted you to remember X sub L over R in series, because of this reason. Okay. So if you have this, and you have that, you can find that. Okay. So at F1 in a series circuit, or in a parallel circuit, at F1 the circuit is acting what? Yeah, it's acting inductively, which means that the current of the inductor's branch is bigger than the current of the capacitor's branch. Which makes sense because at our capacitor at low frequencies is an open. Okay, at low frequencies is an open. So if at resonance I've got a low amount of current, right? Because those two branches have a circulating current. I have low current at resonance, which means that resistance is at its max. So low current, impedance is at its max. Okay. That's really it for the parallel lesson. It's just like the series, except that chart turned upside down. You got the circulating current and you've got R in parallel. Okay, which is the equivalent to that winding resistance of the inductor. Okay, so you have in series at resonance, the voltage of the reactive components was how many times bigger? Remember there was that other way we could figure out the voltage of the X sub L and X sub C? We could multiply the generator's voltage by Q, remember that? Okay, well at resonance, the circulating current, we can multiply the resistor's current by Q, okay? So the voltage at resonance in series is Q times bigger, and in parallel, the current is Q times bigger. All right. Well, we said that at F1 in series, that it was acting capacitively because X sub C was bigger. Right? Because at F1, you're coming from 0 hertz going towards the frequency of resonance. So you're still at the lower end of the band. So the inductor is more of a short than the capacitor is at the low frequencies. Okay. So, but in parallel, at 0 hertz, this is a short, right? And if I have, let's just say 120 volts, that is common here and it's common here, right? So, and it's common here. But I've got no current here. So in a parallel circuit, we want to know what current is bigger. This current is bigger. I've got no current here. So the total current is going to have what kind of an angle? Negative. Right? Because this is X of L at positive 90. When you divide it into a voltage at 0 degrees, if this voltage is at 0 degrees, this is X of L at positive 90. So this current is going to be bigger. Let's just say at F1. So this current is going to be bigger than this current. And it's going to be bigger than this current by the value of this current, whatever this current is. If I've got 1 amp here, in here I'm going to have 2 amps, and here I'm going to have 1 amp. This is minus J, and this is plus J. So that when I put this in rectangular form, the total current, 1 amp minus J, 1 amp, then I've got a triangle. 1, 1. Right? Pythagorean theorem, a squared plus b squared equals that squared. Right? 1 squared is 1, 1 squared is 1. The sum of those two is 2. So this length is the square root of 2 times bigger. Total current. And it's got a negative 45 degree angle because this current here is bigger than this current minus J. This is at a negative 90. So now I've got a total current for the circuit. I no longer have a circulating current. I've got a total current for the circuit that has a negative angle. When I divide it into this voltage, I'm going to subtract the negative angle, which is going to make Z total have a positive 45 degree angle. Okay? So if total current got bigger by the square root of 2, total impedance got smaller by the square root of 2.